Okay, last time we were more or less at this point, so we have seen the first examples of a description by the time diagram of transmission, packet transmission from one source to a destination, and also with an intermediate node using the store and forward node. And we also looked at the differences between different queues as output queues when you have packets that are going to different destinations, or when you have packets going to the same destination. So, as you can see from, for example, this diagram, here there is an extra delay that is experienced by the second packet inside transmission delay, transmission time, and the transfer delay, propagation delay. This is due to waiting, so waiting delay. It's the queuing delay. And the queuing delay is derives from the statistical multiplexing of the packets in the output queues. So it's due to the asynchronous arrival of the packets. When more packets are going to the same output queues, one is goes into transmission, while the others have to wait in the queue. This is a small video example where you have this animation where you have two different queues. In this case, there is only one inlet to the queue, but you can imagine that this is the result of putting together all the traffic that arrives to the node. And the rate or the average occupation of the queue is related to the speed of the packets that are arriving and how fast packets are transmitted at the output. Basically, if the speed of the rate of the packets arriving at the queue on average is less or almost equal to the, or at most equal to the rate of the packets that are, sorry, if the rate of the packet is faster than the rate of emission of the packet is faster than the rate in the output, then the queues gets congestion, and if this is true on average, so on average the emission rate, the rate of the arrival of the packets is larger than the transmission rate at the output, sooner or later the queue will get full, regardless of the size of this. Instead, if on average the arrival rate is less than the transmission rate at the output, the queue remains empty, or maybe you have a certain average occupation, but it's stable. Okay? So this is a stable system, this is unstable. When you have a queue, you are able also to face or to withstand temporary increase of the arrival rate. So if on a limited time interval the arrival rate increases a lot, it may also increase above the emission rate, then this queue will get it will get full, but if this is only temporary and on the long period, on average, the emission rate or the arrival rate is less than the transmission rate, the queue will be able to withstand this temporary congestion because then it will empty again. Okay. There is a theory that is a queuing theory that allows to us to derive or predict the queuing delay on the basis of the parameters of the queuing system. Queuing delay is a random variable because it cannot. It depends on the state of the switch of the queue, and so you cannot know in advance what is the state forever, but you can only predict the results on the basis of some average measurements. And there are several systems with different parameters that are studied in the queuing theory. We will not go into the details in this course, but I'd like just to mention the simplest queuing system. It is a system where you have, like in the previous picture, a single entry that collects all the arrivals of the packets to the queue. They can make up different inlets from different inlets, but they are considered as an aggregated of packets. And then you have a single server that is the transmission system, so a single transmitter. And in order to develop these simple formulations, we initially assume that the queue is of infinite capacity, infinite size. So if R is the average, is the input rate, this is the rate of the transmission of the output link in bit per second. L is the packet length, and lambda is the packet arrival frequency in packets over seconds. You can define traffic intensity as the ratio between L multiplied by lambda divided by R. Okay. These quantities can be usually the link rate in the output is constant because it will change over the time of the transmission system. While the packet length and arrival rate can be random variables. Can be variable. Especially in the internet case, you will see that length as the packets have different lengths. So it is random variable. When the traffic intensity is small, we expect a small queuing delay, while we expect that this queuing delay gets larger when this traffic intensity increases. Okay. And if we develop this theory under some assumptions regarding the arrival process and also the distribution of packet lengths, not get into the details of these assumptions, but this is not true for every system, but also for specific systems. Then the result of the queuing theory is like this. So when the traffic intensity is zero, queuing delay is zero as expected. When you increase traffic intensity, the queuing delay starts to sharply increase, and when the traffic intensity gets close to 1, then the queuing delay has to go to infinity. Okay. So it means that when a new packet arrives to the queue in these conditions, the queue is of infinite capacity, so the packet will not be lost, but the time the packet will reach the transmission system tends to infinite. Yes.
Why determines the part and not the
because you are basically, as we said before, the congestion depends on the ratio between the arrival rate and the output rate. So when the arrival rate is less than the output rate, then the queue remains stable. When the arrival rate is larger than the output rate, the system is unstable, so you cannot even apply this. And the threshold is 1, when the arrival rate is equal to the rate at which packets leave the system.
So the traffic intensity is in the number of packets. Traffic intensity.
Traffic intensity is does not have any size because it's a ratio. Here you have bit over a second. Okay. And above you have
bit over seconds.
Yes.
So after doing this omitting, we can have a number of paths.
You have a fewer number. Here we say that packet length is bits. Actually, if you want to be precise, you should write bits over packet because there are bits per packet.
Bit per packet.
Okay. So if you try, if you put that the unit of measurements in the ratio, you obtain a fewer.
So it's unitless.
Yes. 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 You have the link, the packet length that is bit over packet. Right. Then here you have the arrival that is packet over second, arrival rate. And here you have
bit per second.
Bit per second.
So it's unitless now.
Yes. So now we can also introduce another parameter, which is the ratio between this is again a random variable. Is the ratio between the rate of transmission and the average length of the packets. This gives you the inverse of the average transmission time of the packet. Okay? And if you replace this new parameter in the previous equation that we showed in the previous slide, you obtain this. That is another way to write down the average waiting time in the queue. It's the same as before, but with this. This obviously, as I said, holds in the case you have an infinite capacity in the queue. When the queue is of limited dimension, if the queue is congested and new packets arise in the queue, then the packets are lost, okay, are discarded. So when we want to implement in an effective way packet switching, we have to provide the system with some kind of protocol that is able to manage the packet loss, basically. And we will see then how this protocol is implemented in the internet network. Okay, so we will get back on this concept later on. Now I would like to cover the final fundamental concept that is related to the internet systems that concerns functional models. This includes a lot of theoretical concepts, communication service protocols, so service primitives, and the concept of a layered architecture. And this is the final point of view through which you can look at the internet system. So what is the communication service? We have already introduced it. When you have two remote entities, that means the implementation of subsystems that are far away, at a certain geographical distance, and you want to exchange data between these entities, so you want to establish a conversation. We can describe this communication as if the entities are requesting a service from what is below, that is the network system. Okay? And the network system is providing a communication service to the entities. This communication service is the transportation of informations at a distance. Okay? So in order to have this information exchange, we need some way to manage this exchange. And in the context that we are looking at, information is always arranged in terms of information units. So finite sequences of information that contains data to be transferred, and can be of different types. So for example, it can be application messages, can be multimedia flows, simple group of bits, or even bits themselves. And the type of information unit that we have to transfer depends, as we will see later on which level we are referring when we are talking about entities, okay, which layer. When we are implementing the communication service, we need functions that enable these entities to call for the service, so to ask for the service to the system that is below. And these functions are called service primitives or service calls. So the entity, each entity is interacting with what is below, the system below, in terms of service primitives. And by these primitives, the entity can request in a suitable way the service to what is below, and it can then receive data or information that has been transferred, or answers to the from the system. So information primitives tells what information to transfer, what is the destination, and what is the type of service that these entities are requesting. For example, we have already talked about the sockets and the application programming interfaces that are implemented by a certain programming language. These are the embodiment of the service primitives that are used by a software in order to ask to the operating system of its computer to set up a communication. It's an example of complex service primitives. So if we want to visualize this concept, you have the two entities that want to set up the conversation in order to exchange information. They have to interact with the other components of the system that are below them, central below. And this interaction is by the service primitives. Then, by, for example, the entity A, by service primitives, can ask the system, the rest of the system, to set up a bidirectional channel with entity B. And the entity B is informed of this. Entity B replies that, for example, in fact, sex is the setup of the channel, and entity A receives an OK from the system to send data. Then this channel can be used to transfer data. And what I have described is typical of all the services that are so-called connection-oriented. So it requires an opening phase transformation, information transfer phase and connection closing phase. With these kind of services, service primitives are complicated. We will see that in the connectionless case, that is also possible. Service primitives gets simpler. Once we have introduced this vision of entity that is interacting with something that is below by a service primitive, in order to set up a conversation with a remote entity, next step is to introduce the layer concept, okay, which is the layer concept is evolution, the expansion of this to generalization of what I said. So the entities that are setting up a conversation, say they are A2 and B2 in the two remote locations, are interacting with something that I define the system below. But what exactly is this system below? We can imagine, it's quite logical to think that inside the two remote sites that have to be connected, we have some entities that are communicating with the first two entities that we have defined. Okay. These entities provide the communication service that has been requested. But the two entities A1 and B1 now, how can they provide this communication service? They need to set up a conversation between themselves in order to exchange. How to set up this conversation? Themselves will need to interact with the rest of the system below. So this concept, this relation can be replicated in an iterative way. And each time you have entities that want to set up a conversation, in order to do this, they use the service provided by entities below, which in turn have to set up a conversation with themselves and so on. So we can say that what we have identified as a couple of entities, A1 and B1 and A2 and B2, belong to a same layer. Okay, so this is the concept of layered architecture, where you have a layer on the top that is interacting with the layer below in order to obtain the service. The layer below, in turn, is interacting with another layer below in order to obtain the service, and so on. Each layer interacts with the layer below with the service primitives, and the entities of each layer interacts each other, the remote entities, by a conversation. The conversation implies the exchange of data, and at each layer you have a particular data unit that is exchanged, that is called protocol data unit. Why is it called protocol data unit? Because the conversation at each layer occurs according to rules that are given to by a specific protocol. So each layer has a conversation and a protocol. It's quite complicated, but then you will see it with layer by layer. It will be much more understandable. So each time a layer delivers a communication service to the layer above, each layer introduces some new functionality. Okay? So the layer 1, that is here the layer of entities A1 and B1, takes the communication service from the layer below, each entity performs some function in order to make its communication service more complete, and then this layer 1 provides communication service to layer 2. Layer 2 will benefit from the extra functions that are introduced at layer 1. So the entities of a layer cooperate to provide the communication service to the layer above, and they exchange the messages, so they set up a communication exploiting service offered by the layer below. The protocol is a set of rules that we have to use to manage a conversation between peer entities of the same layer. So the protocol is always used for the horizontal arrows that you see before. Why we need a protocol? Because we have to specify what is the format of the messages that these peer entities exchange, what is the type of information that is contained in the message, the service information, how we have to manage transfer of this information when we have to send a message, what is when the other entity has to reply, and so on. This is all contained, specified by a protocol. And as I said, the protocol specifies, first of all, the format of the information that is transferred, and so it specifies the format of the protocol data unit. It is the unit of data that is transferred at that specific layer that is managed by the protocol. Each protocol data unit is composed of two parts. One part is the so-called payload, and the other part is the header. The payload contains the information that has been transferred, that have to be transferred at that specific layer. The header contains extra information needed to manage communication at that specific layer. So the actual content of information is in the payload. The header contains only control information. So information that is only used in order to control communication. So when we are talking about layer architecture, we refer to the architecture of the whole communication system like internet, and sometimes we call it also protocol architecture, because each layer is associated to a specific protocol. We say that this relationship between layers is iterative or recursive, but when does it start and when does it finish? Because of course we have to put some limits. So usually what is called the layer 1 or physical layer provides the basic communication service, the simplest as possible, that is transferring signals or bits in terms of electromagnetic signals or signals in general on the communication systems. Okay. So this is the simplest layer because you have only to deal with protocol data units that actually are the bits themselves. When you go up, you start increasing functionality, and the final layer that we have in the internet layer architecture is communicating to the applications. It's taking data and releasing data to the applications. Each time a layer transfer information in terms of protocol data unit, this information, we start from the sender, on the left, let's say layer 5. This information is given by the sender to the layer below. The layer below takes the information from the layer above the protocol data unit of layer 5 becomes the payload of the protocol data unit of layer 4. And layer 4 adds another header, which is the header at layer 4. Then, this is recursive, so each time we go down on the sender, layers adds headers and takes what is released by the layer above as a payload of the protocol data unit. So at the end we have a protocol data unit that contains many headers and some payload. This is transferred on the network, on the physically transferred on the network. The receiver takes everything at the lower layer and then the history repeats on the other direction. So at each time a layer receives a protocol data unit, it cancels the header related to that layer because it's not useful anymore. What is the remaining of the protocol data unit is given or provided to the layer above. Okay. That will apply the same. Okay. So finally, we will have the original information that was released to the system. What are the advantages of this apparently complicated architecture? There are several advantages, and in fact, the layer architecture has been one of the reasons of the success in communications. We have a very complex system, but if we partition it into different parts, logical parts, we can easily identify the service that is given by each part. We can manage each part, update it in an independent way compared to the other parts, and so all these advantages makes it a winning architecture. For example, if we think on the updating issue, you can change a protocol at one layer because you want a new protocol. You don't have to touch the other layers. The protocols at the other layers remains exactly the same. Sometimes this can be a disadvantage, and for example, when you have conflicts between layers, we will find maybe later on. So, in the specific case of internet architecture, that is also called TCP/IP, protocol model, all the layers have names. So, the top layer is called the application layer. Then you have the transport layer, network layer, data link, and physical layer. So in the application layer, the protocol data units that are exchanged contains as a payload the information that are coming from the processes. Okay. So the application layer is interacting with processes. And the protocol data units of the application layer are called messages, application layer messages. Okay. In the transport layer, these messages are encapsulated into a transport protocol data unit, adding a transport header. Transport protocol data units are called segments. Segments are encapsulated into packets that are protocol data units of the network layer. And here you have the so-called IP protocol. This is why, because it's very important. So this is why it appears in the name of the whole architecture. And also in the transport layer you have the TCP protocol. This is why TCP. Then packets are encapsulated into frames. Frames are the protocol data unit of the data link layer. And finally, you have the physical layer where information that is transferred is bits. Okay. So this is basically the TCP/IP stack, protocol stack or architecture, and we have to notice that actually the TCP/IP protocols are specified only in the application, transport, and network layers, while the data link and the physical layer are not part of Internet specifications, of Internet standardizations, documents that are called recommendations that specify the protocols. And this is because, this is the concept that we have already introduced, Internet is a network of networks. And so it was developed to interconnect networks that have different technologies. And network technologies in the local area are specified by the data link. Okay. This is why Internet standardization does not get into the data link. For data link, there are other standards. And the Internet stack is able to interface with networks that are based on different data link standards. In this course, I will show you briefly, because time is very short, but I will show you some tools that allows you to visualize the main concepts. And one is called the Wireshark. It's a freeware tool. It's called also sniffer, packet sniffer, because it's able to copy all the packets that flows on an interface, usually your PC Ethernet interface, either wireless or wired, and analyze these packets. Okay, so if we have a quick look at this tool, just to give you an idea. This is the analysis of a set of packets. Oops. Actually, these packets have been all stored in a file, so it's a prepared capture. And you can see let's take, for example, one of these packets. Let's say this is an HTTP message. HTTP message, we will introduce it during the next lesson, is a message of a application layer protocol, which is called the HTTP. And here in these lines below, you find the analysis of the packet that is selected. Now I have selected this packet here. So here you find analysis, and it's done layer by layer. The top layer here is this one, where you have a hypertext transfer protocol, that is HTTP. And if you click here, you can open this, and you can have a look at the content of the message at the HTTP layer. Okay. This is the protocol data unit at HTTP. Also, the application layer introduces headers. So actually, what you see here at the beginning on the these lines is the header that is introduced by HTTP. We will see what is the meaning in the next lessons. And then you have the content. In case of HTTP, the payload that is carried in the message is an HTML file. In fact, if I close here, you can see you have also the possibility to have a look at the file. This is an HTML file that is transported in the HTTP message. Then this HTTP message is carried in a TCP segment, which is the Transport Layer Protocol Data Unit. And here you can see all the fields of the header of the segment. This segment is carried in an IP packet. Here you can see the fields of the header of the IP packet, which is the Network Layer Protocol Data Unit. And finally, the packet is carried into an Ethernet frame, which is the protocol data unit of the data link layer. Okay. And for example, here you can see the MAC addresses that are written into the data link frame in order to identify the source and the destination at data link layer. If you inspect the IP fields, here you can see source and destination IP addresses 216.239 and so on and so forth. Okay, these are in the header of the IP protocol. So this is just to show you some so we have to to go to the final concept. What is, so we introduce the concept of the layers. We say that each layer introduces a function, some functions. With these functions, make what is delivered to the upper layer richer in terms of performance than what is released to the lower layer. So, what kind of functions we can implement in each layer? Actually, there are many. That depends on the different layers, but these three functions can be found in can be implemented with different results, but at various layers. So they are, let's say, the most important in terms of concept. Again, here you will look at abstract definitions that don't tell you so much, but then when we will talk about the implementations of specific layers, you probably will recall these definitions and understand them better. So the first is called the multiplexing and demultiplexing. We say that a layer entity is communicating with lower layer entities by the functional the service primitives. This communication occurs in a specific points or logical locations inside each system, and these locations are called service access points, and usually are represented this way. Okay. So, what if you focus on a specific on the entities of a specific layer in the sender and the destination, the two remote sites that are in communication. Level N takes information from the level above and releases information to the level below. And the blue circles, the blue ellipses, represents the service access points. The service access points connecting level n plus 1 to level n and level n to level n minus 1. Okay. Now, these service access points may be unique, as in this case, but they may also be multiple, okay, as what we see above. Okay. So, when you have multiple service access points, it means that the entity at level n, in this case, is receiving information by multiple entities at level n plus 1. Okay? So imagine that, for example, on the left you have entity A at level n plus 1, entity B and entity C. This information has to be taken and delivered to the rest of the system in order to be transferred to the remote entities. And if on the communication between level n and level n minus 1 is on a single service access point, it means that the sender has to multiplex all this information on a single connection. Okay. When you arrive to the receiver, this information has to be demultiplexed so that these entities at level n deliver the correct information to each entity at level n plus 1 to which they are connected. Okay. So we have the multiplexing operation and the demultiplexing operation. In order to perform this operation in a correct way, you must identify these service access points in some way. So you must give them a label so that when, for example, the receiver receives all the multiplex operation, entity at level n knows exactly where to send, which specific service access point to send the information that has been received. So this is a concept that you can apply at different layers. In particular, just to give you an example, it's what happens at the transport layer. Okay. When you are transferring information for example, from a server, a client to a server. For example, when you are connecting your computer to the network, in your computer, you don't have one process active. Okay? Maybe you have different applications. For example, you have an application for email, an application for web browsing. These applications are active at the same time. Your PC has a single service access point to the network because you have only one Ethernet interface you are using. And this is identified by an IP address that we will see later on. Then you can imagine that you are interacting with one server. Maybe they are two separated, but just to simplify, you are interacting with one server machine. This has a unique interface with the network that is represented by or identified by another IP address. But here you have web browsing and email. So your client application for web browsing wants to talk only with the client for the server application of web browsing that is running on the server. And the email application wants to talk with the server side of the application in the server. But they are active on the same physical machine. So how to identify the different flows? You need to introduce identifiers from at this level, so that when you are releasing data to the applications, you are addressing the correct application. And this is done at the transport layer by introducing core numbers that surely you have already seen somewhere. Okay, so, for example, the web browsing is identified by port number 80. Email is identified by port number 25. Okay. So this is an example of multiplexing and demultiplexing. The other typical function is error control, because nothing in real engineering is completely error-free 100%. It's impossible. So you may always have errors while you are propagating information, also in this case. But the service that is required by certain applications must be completely error-free. So you have to introduce functions that are able to cope and solve the problem of errors that are that occurred during transmission. This is the error control, and it can guarantee reliability of communication to the applications even when the network below at the physical layer, for example, introduces errors. How this error control function is usually implemented? First of all, we always talk about protocol data units, so finite strength of bits or packets, or they are named in different way, but the concept is packet. So when the sender sends the packet to the receiver must be able to check, to understand from the packet that has been received is if an error occurred during transmission or not. Usually this is possible because when the sender sends the packet, it introduces redundant information. So extra bits are not useful to create the original packet protocol, but they are added so that in reception, the receiver can check if some error has occurred. These bits are redundant. The concept is, for example, what happens with the parity check, that is very common in computers, and maybe some of you knows about the so-called error blocks, so the block encoding for the error control. So when so the receiver is able to check the error and then understand if the packet that is being received is error-free or is not error-free. If the packet is error-free, usually you don't. If the packet is not error-free, so if there is an error, usually don't try to correct the error. The receiver drops the packet, and the packet must be transmitted again. This is the simplest way to perform error check. So the packet arrives. If the packet is correct, so nothing, no error has been has occurred, then the packet can be sent to the upper layers, okay, to the layers above, inside the receiver. Since this mechanism is based on the retransmission, the sender must be informed in some way if the transmission of that packet went well or not. So if not, the packet must be retransmitted. So usually the best method is that when the packet is received correctly, then the receiver sends on the back channel, back direction channel, an explicit message that is called ACK, so acknowledgement. And this message tells the sender that the packet has been received correctly, so it must not be retransmitted. Okay. What happens if this message is not, if the packet is not is corrupted, so there's some errors. So the packet is dropped, and now here we have two choices. The first is that this receiver informs with another message the sender, and this message is a negative ACK, so it says, look that the packet is being corrected. But there is another alternative, that is the sender does not send anything, the receiver does not send anything. So does not send an ACK, it does not send also a negative acknowledgement. And this is the safest way, because when you send a message back, also the message that is sent back may be affected by errors. So the simplest way to implement error control is that when the sender sends the packet, it starts counting the time, and if the packet is not acknowledged by receiving an acknowledged message on a specific time, then, in this case, when the packet is dropped, so nothing is sent, then the packet, the sender does not receive anything. So if the channel remains silent for a certain time, then the packet is automatically retransmitted. Okay. So you have a retransmission. This is the retransmission based on the timeout. We will describe it later in a better way. So here you see the simple block diagrams that implement the two functions in the receiver and the sender. Negative acknowledgement method is also possible. So when you check that the packet has no errors, you send an ACK. Okay. When you check that the packet has an error, you send a negative acknowledgement. That is an explicit message. However, it's more complicated, and it requires that the receiver is able to correctly identify the packet that is corrupted. Okay. When the receiver receives a packet that contains an error, the error can be anywhere in the packet. So it can be also in the header. So it means that the receiver is not sure about which packet contains the error. So this is why the timeout across the method is easier, because if the packet is dropped, the receiver does not do anything. If we want to implement the negative mechanism, the negative acknowledgement mechanism, the receiver must identify what is the missing packet or the corrupted packet. So it can only, if the packet is an error, this packet is blocked, and the receiver cannot do anything because it is not sure about the identity of the packet. Only when the receiver receives another packet and the packets are in an ordered sequence, then it can understand that the previous packet was lost. So in this case, when the next packet is received correctly, the receiver can send back a negative acknowledgement. By receiving a negative acknowledgement, the sender will transmit again the packet that has been paid. So this is the other function that we are introducing. Last, the routing function. Maybe it's easier to understand. So imagine that the packet arrives to an entity from the upper layers, and again we have this situation where we have multiple service access points from a layer to another layer. Okay. So entities that are at this layer must decide what service access point to use in order to send this packet. Because here we have multiple entities attached to the single entity. So this is the routing functionality. Inside the packet, these entities must find information on where to send this packet. We have already introduced the difference between datagram and connection array or virtual service. In any case, it's a packet that carries data about that helps or that are used by these routing entities to decide where to release the packet. So once this information is flagged by these entities, For example, by reading the header, then the packet is sent to a specific service access point. This is the case where when these entities receive the packet from the upper layers. But there is also another case if these entities are inside an intermediate node, the packet may arrive from the lower layer. It will arrive from one specific access point, service access point. These entities, however, has to process the packet in the routing sense in the same ways as before, because now the packet must be sent again to the lower layer, but there are multiple choices. There is a multiple choice. There are several places where to send the packets. So again, we have to look into the information that is carried by the packet, compare this information with the local database, information that is owned by the entities, and then select the output port. So the routing function is the same as before. Okay. So when the packet enters from the level below, we say that it enters from an ingress port. It has to be released again at the same level. Okay. So the only function that is performed by the most important function that is performed by this entity is routing. But this entity or this layer does not release the information that is contained to the layers above, because this is an intermediate node. So it will release again to the layer below on the suitable interface. So in an intermediate node, you don't need to implement all the layers. You can just implement the layers up to the level, the layers up to the layer where you have to implement the routing function. So, for example, in a router, which is the intermediate node of the internet we have already introduced, the routing function is performed at the network layer because the router manages IP packets. Okay. So in a router, you don't need to implement the upper layers. You don't need to the transport layer and the application layer. Transport layer and application layers must be implemented in the host, both in the client and in the server. So what happens is that in the sending host, the information is encapsulated and released on the network. When it arrives to the first intermediate node, that is the router, the router implements only the physical layer and the upper layer. So the IP packet is processed in the network layer, and the main function is to find what is the next router or the next interface where to release this packet. And this is repeated until the packet reaches the destination, that is again a host. In this case, the destination is the network layer release information to the transport layer and to the application layer, but not before.
So I understood that if the information packet is not directed to a certain terminal, it doesn't reach to the transport and the application layers, and it just merges into the other route.
The packet is never reaches the transport application layer until it reaches the final destination, that is the host. In the routers, you don't need to process the packet in terms of network and application layer. And this is true for all the Internet of Things equipment. The router is the equipment of the device that is operating routing at layer 3, so the network layer. But in other cases, you have the switch that is implementing routing at the data link layer, and the same applies. So when you are crossing the switch as an intermediate node, here the packets are only processed at the data link layer. You don't need to implement the network layer, the transport layer, and the application layer. So in the switch, you have only these two layers. And then the packet is processed in this way until it reaches the destination. There is also the possibility to perform routing at the application layer. When you perform routing at lower layers, the operation must be simple. So the switch performs very simple operations. The IP router is a little bit more complicated. Proxy allows you to perform routing, but also complex operations, for example, like application or traffic classification, filtering, control of the identities of the senders and of the receiver, and authentication and so on. Okay. In this case, you need to implement, of course, all the layers until the application layer. But the proxy is not like a host, so it doesn't have to send the information to a specific application process. But it's always an intermediate node, so a routing node. So it will forward this information to another proxy or to the final destination. In the routing function, there is another component that is important to understand. The routing table is what you need in the router to perform, to decide on the destination on the basis of what is written in the packet. So, but the packet is written, is prepared by the sender, but who is writing these routing tables? This is the other side of the story. The routing tables are written in different ways according to what is the type of control mechanism that you use for your network. So, for example, routing tables can be manually compiled, maybe also remotely by an operator, but still in a manual way. So, for example, you send packets on a certain path, and then when it is manually modified by accessing to an intermediate router, the path may be changed. This has the big advantage that it's limited in terms of scalability. You cannot have thousands of operators manage the network, and also in terms of intervention time. If something happens in the network and you want to react to, for example, to a failure, the human intervention is not very fast. So the other way to do this, to rewrite the routing tables, is in a distributed way and automatic way by letting the routers to talk each other, to exchange information about the network state, and automatically write down the routing tables. And we will have a look at this. And then there is a final way to implement the control plane, called control plane. This is centralized, and all the routing tables are written by an external controller. This controller can be controlled on its turn by software applications. And this is the new way to implement the control that is called the software-defined network. So, compared to the distributed case, has the advantage that you can easily change or update the algorithm that you use to optimize the network and to optimize the routing. So this is basically the end of this part. As I said, it's quite theoretical, but so in some sense also a little boring. But you will understand it later on. And I wanted just to show you another tool that you can use and helps us in visualizing what happens in a network. And this is called the Packet Tracer. It's a tool that is provided by Cisco, mainly for teaching purposes. You can download it from the site that I have already sent you by email, where you find also the other tools that we will use. In this case, it's better to download it if you have Windows. It's the best, because with Windows it works quite nicely. So it's better to download it separately from the virtual machine that is instead used for the other for the other tools. So now I will try to show you how we can use it in a very simple example. Sometimes it crashes, so I won't crash this time. And unfortunately, I don't have a very good. Well, it's quite visible. Okay. It's a little bit small because I have a high resolution screen, so it's hard to see everything. If you want to repeat this simple experiment, I have put on the beep the files that you need to open in order to have these elements already pre-configured, okay, so that you can easily set up the network. So this is a set of components or devices we have already introduced. And here in particular you have, let's focus on this part, the part on the right and below. You have a PC and a server, so two hosts. By this software you can emulate the network. So basically all the components or the equipment that you see on the screen corresponds to a process or a virtual machine that is running and is actually performing the same functions that you would have in the real thing. Okay. So now we can start in a very simple way to connect this PC with the server. So I take the connection tool. Okay. So now they are connected by a point-to-point link. You have already seen that you can connect equipment using different type of links, and one is the point-to-point. And we can look at the PC. If you click on this icon and you go to desktop, basically this is the same that you would have in your PC. So you have a desktop with some applications. So let's try to open the web browser. Okay. So in the web browser, we can, for example, ask the server that is connected to send us a web page, and we will see later on what is exactly the meaning of what I am writing. But basically, this is a web page, so you can write down a URL is the identifier of the page you want to obtain. For example, www.polyme.it/polytechnico. I hope to write it correctly. Okay. Now imagine that we are inside the campus of Politecnico, and we want to connect to the Polyme website. So, it takes some time because the system is a little bit overloaded. And now in a few seconds you will have the access. This is the home page that is being received by the PC from the server and contains an HTML document. Here I just cut all the graphical part because otherwise the system crashes easily. But okay, you can imagine the rest of the page. In case this document is being received to the PC. Obviously, we don't want to have a single connection from a server to from a client to a server. We want to implement okay. We want to be able to log into the server and use the server by different clients in the same way. So we are in the local environment inside the campus. We can use the hub. This is a network equipment which can be used as an intermediate node in a local area network. Okay? So from the hub, we may connect for instance these two PCs, PC1 and PC0, to the server. Okay, so one port of the hub is being connected to the server, the other two ports to the two PC. And we can show that the two PCs are able to interact with the server in the same time. For example, here, this is PC1. We can open the same. The same page as before. No. Okay. And then we go to PC0. This was PC1, this is PC0. We can do the same. Okay. So you can see we have the two independent communications between two clients and the same server. Okay. This server is able to manage communication with different clients through the same port. So we have the multiplexing example that we have mentioned before. Identify obviously each client, which is making a request in order to send the proper information as a reply. And we will see later on how this is possible. So we are still inside the campus of Politecnico. Now let's imagine that we want to we move to a different place. For example, a company network, an intranet, and here we have another server and other two PCs. We want to connect them. Again, we can use a switch, which is another equipment you can use for local area networks. Okay. So we have this PC3 and PC2 connected to another server, different server. So let's open the first of the two PCs. Imagine that you are in Cisco. This is the company who is managing the intranet, and you want to access to a Cisco page, for example. Cisco.com hello or this is H. Okay. So this is a very simple page. We retrieve it from the server, and on the other side this is another page. Okay. So beautiful, we have two networks, and we can access from, we can obtain web service in one network and the other one at the same time. But imagine that now in Cisco you want to access Politecnico web server. Okay. How can you do it? Obviously you don't, you're not able to access it because this is a local network and there is another local network. So this is when the router comes into play. The solution is to use a router to connect the two networks. Okay. So you have two different local area equipment, different devices. In this case, they are both supporting Ethernet, but you can imagine that you can use completely different technology. And then the router is able to establish a communication between one network and the other one, because you are creating the network of networks. Let's test it, hoping that it works. So for example, here from this PC, we want to access Politecnico on page. Okay, yes. Okay. Now we are in PC3, which is located here. So in the local area network of Cisco, and from here you can access this server that is down here. Okay. So this is a very simple test case, but just to clarify the concept of the internet. So tomorrow we are going to make a short exercise or some few exercises on this first part, focusing on packet switching, and then I'm going to start the new chapter of the course dedicated to application protocols. Okay. See you tomorrow. Thanks.